Good afternoon. A couple simplification problems up here to kind of start us off today. All right, I want to see where those go. So jump on in, see what happens with them. Not a lot of folks here today. Hope everything's okay out there. Okay, Andre's not going to be here today. Justin, okay. Took out a couple notes from people. Clutch cable snap going down the road. That's terrible. I'm glad you're okay and that didn't happen in some terrible way that caused some sort of horrible accident. But that does sound very troublesome. Excuse me. So hopefully you've been practicing these. They do take some practice, and the manipulation that we get used to in practicing them will be helpful as we go along. I do want to talk about, start our conversation on solving today. But if there are any others of these that you've been playing with or fighting with, do bring them up. Let me know. I'd be happy to look at them specifically. These can kind of be little individual puzzles on their own, so they can, sometimes just a small change can make for a problem that's a lot tougher to get a hold of. So Excuse me. Well, that's up to 6 people. That's not too bad. You know, the class does have 20-something people in it, but 6 is what we usually seem to get. Yeah, there are 22 folks in the class. We usually see 6 or 7. And a lot of respect for you 6 or 7 who do come here and put in that time. Hi, Nicholas. We're just trying a couple problems, making sure we're all doing okay. Well, Garrett, you're assuming they're doing okay in their grades. And there are some that are not coming here that are doing fine. There's a big batch that I don't see much of and don't get much homework from, and their tests did not go well. So yeah. But maybe we'll start seeing more of them after, class starts to get late and it turns into kind of like, oh no, maybe I should start doing stuff if I want any hope of being successful. So in a minute or two, I'm going to ask you guys what suggestions you have for approaching these. So be ready for that. I don't think that first one's going to be too bad. That second one's got some nasty to it, but kind of depends again on how you approach it. So we'll see. So let's see. Any particular suggestions or things you tried, whether they worked or didn't work, to start number one? It is actually particularly nice to look at things that didn't work, try to see why. But either way, what was somebody's first approach or first step in trying to manipulate this first one? or any observations or thoughts or. Now, certainly there are some reciprocal and quotient identities we could grab. Got messy fast? It can. But let's go ahead and take a look at that. What had happened? What would happen if we did that? Anything we notice? So cotangent would turn into cosine t over sine t if we looked at its quotient identity, or 1 over tangent t if we looked at its reciprocal. Cosecant would turn into 1 over sine t if we looked at its reciprocal, and sine t would be 1 over cosecant t if we looked at its reciprocal identity. Now, we certainly wouldn't make all these changes all at once. That's one of the things to be careful of. Sometimes if you change too much at once, you miss some nice interactions. But this is kind of what you want to have happen when you look at a problem like this. You almost kind of want to see these floating options around your problem, or out, whether it's, visual or just conceptual. When we see cotangent, we know we've got some options for how we think about cotangent. Same with cosecant and sine. And the thing that stands out in thinking about those is both cotangent and cosecant have that sign in a denominator depending on how we look at it. So this already is a sine. These two have sine in a denominator. So it might be handy for us to use that sign to try to simplify some of this. Now, let me put back my cosecant. So seeing that sign, if we multiplied cotangent by sine t, the sine t would cancel with the sign in the denominator of cotangent. If we did that on the bottom, we'd have to do the same thing. Sorry, if we did that on top, we'd have to do the same thing on the bottom. So whether we convert it into all those reciprocals and quotients, or we just use them as a way of planning our actions, either way, we should get some at least ideas of how to proceed. So when we multiply that sine by that cotangent, again, since cotangent is cosine t over sine t, when we multiply that sine by the cotangent, the sines are going to cancel. We'll just get a cosine on top over sine multiplied by sine is going to give us a sine squared t. I never liked t's as a variable. Oh, it just looks weird. And cosecant times sine, here's the big one. Cosecant times sine, well, cosecant is, again, 1 over sine t. So if we multiply sine by its own reciprocal, we just get 1. So if we tried to look at all those options at once, if we tried to make all those transformations all at once, it could get a little messy. But keeping all of those options in mind can lead to, hey, here might be a nice way to handle it. Having done that, anything nice we can do with this 1 minus sine squared? Cosine, I'm just going to say that's cosine squared t. So yeah, that turns into a cosine squared t with a cosine t on top. That cosine t is going to cancel with one of those cosines. And we'll be left with 1 over cosine t. And if we like 1 over cosine t, great, leave it. If you want to write it as just one trig function instead of a trig function in an expression here, we could rewrite that as secant t. And all that stuff's equal to secant t. Questions about that? Other observations about that? Anybody take a dramatically different approach? There are certainly other different approaches you could take. There are always other approaches you could take. That's what makes these both fun and challenging. I know it's hard for me to make sure you guys are being active about these in this format, but it really does make a big difference if you guys are out there playing with this stuff and trying these things as we talk about them. You don't want to take the supposed anonymity of this format to be passive in this process. As they say, it all comes out in the wash. So make sure you're fighting with these. And if you're not sure where to start, that's okay. One of the big things about these is being not sure where to start. Trying to figure out things that you could do. Because kind of, we could really do a lot. If instead, say, you went to the whole 1 over sine t and just focused on that, you might go, oh, well, okay, I can get common denominators there. So that common denominator of sine t would mean you'd have to multiply that by sine over sine to have a common denominator in your denominators. That would give you 1 minus sine squared t over sine t. That would give you cotangent t over cosine squared t over sine t. Multiply by our reciprocal, cotangent t times the sine t over cosine squared t. Cotangent is then, by quotient identity, cosine t over sine t times sine t over cosine squared t. The cosines cancel, the sines cancel. We're 1 over cosine again, and still equals secant. That might looks like a little bit of a different pattern, but it's not in a lot of ways. Our logic for finding common denominators was different than the logic of trying to clear out the denominators up here, but we still multiplied by a sine to make the sine squareds. We still ended up multiplying that numerator by sine. The same tools, just a slightly different pattern. So different way to go about it. Same tools, but different path. Anybody do anything else? Again, even if it didn't work is good. We can see why it didn't work or see what happened with them. You guys are being quiet today. Gonna make me do something more weird with it. Samuel tried that way with the common denominators. Let's do something weird with it. See what happens. I don't know how this will work. No idea whatsoever. Seeing cotangent. I don't like cotangent because no, I hate cotangent. I really do. Not for any real reason. Just sometimes it's fun to hate things. But if I multiply cotangent by tangent, that's multiplying it by its own reciprocal. And when you multiply something by its own reciprocal, you get 1. So it's a 1 over tangent times tangent. So that numerator is going to become a 1. And that's nice clean numerator. Maybe we made too much of a mess in the denominator. Maybe we didn't, but let's see. We'll have cosecant t times tangent t. That'll simplify into something. Minus sine t times tangent t. And that'll hopefully simplify into something. Cosecant is 1 over sine t again, while tangent is sine t over cosine t. And this is sine t and sine t over cosine t. So the signs are going to cancel there. That's going to be 1 over cosine t minus sine squared t over cosine t. So that's going to be 1 over 1 minus sine squared t over cosine t. It's going to be 1 over 1 minus, well, why don't I just take the reciprocal of that? That'll get cosine x over 1 minus sine squared x. Cosine x over cosine squared x. So 1 over cosine x, which is back to the secant x. Well, t's. I hate t's. I got a lot of hate in my heart today. So that was kind of a weird way to start, but it worked out. Saying, hey, the tangent will clean up that cotangent and see what else happens. I kind of like that way too, mostly because I don't like cotangents. And it gets rid of pieces. Our whole plan is trying to simplify stuff. So, multiplying in something that gets rid of something else is going to help us simplify. That's part of the reason why that first method of multiplying by sign was so promising to me, because multiplying by sign is going to get rid of that cosecant. So multiply it and see what else happens, and a bunch of other stuff, happens nicely. So, and that's, again, one of the things that can make this kind of tough is the whole, how am I supposed to start this? There is no how you're supposed to start this. It's, well, what do I see that I can manipulate? And that's one of the things that I think makes the second one a little bit, or can, depending on what you see and what you don't see, can make this second one a little bit ugly. But again, depends on what you see, depends on how you start, depends on what your approach is. So anybody have any thoughts on how they wanted to start that or approach that, or anything they saw? Or, one of the things that I'll stress a lot as we go along, but I've mentioned a little bit here and there, is that idea of looking for what you don't like, or looking for, those wouldn't it be nice moments. Like, gosh, wouldn't it be nice if that was a subtraction? Wouldn't it be nice if there was a square there? Wouldn't it be nice if we had another cosine term? Anytime you look at something and go, gosh, I wish something was there, or I wish something wasn't there, Well, think about how you can change it. Think about, what can I do to make this a subtraction? What can I do to make that cotangent go away? Math people tend to end up like that after a while. You just see something that you don't like. You don't just kind of try to work around it. You go, okay, well, how can I make it into something I do want? And that works for math problems. It also works just in life. So what were your thoughts on starting this? And preferably somebody other than Shay or Sam. Maybe I should pick somebody. Who doesn't want to be picked the most? Turn secant into 1 over cosine, Nicholas? Sure, why not? Again, that's part of the point, is the whole, I did tell you guys that I kind of try to think of the turning things into sine and cosine as almost a last resort tool. But hey, if you can't think of anything else, do it. But okay. The question's always going to be, though, cool, very true, very legal manipulation. Now what? Now, Dominic, you have multiplied both sides by cosine. I mean, top and bottom by cosine. I don't know if those qualify as sides, but I know what you mean. So, where'd my pig go? So that's why. So multiply that by cosine t, multiply that by cosine t. I don't mind you guys in the comments saying, COS, but when you're writing these things out by hand, don't leave off the t or x or theta. It can cause you trouble later on. Now, why multiply by cosine? Well, certainly it's going to do similar things to what it did on the other problem, where it's going to make that 1 over cosine go away and give us just a 1. So that's nice. It is going to put a cosine there, but at least it's not in a denominator. And we're going to get a 1 plus cosine squared t. Oops, not cosine squared. Sorry. Not 1. Cosine t plus cosine squared t on top. Okay, that didn't have, so now there are no fractions in our fraction, which is nice. We don't have a secant. But I'm still a little stuck on the now what. I do think, by the way, this is a significantly harder problem than the one before. So I got one more suggestion out there we can try before we start looking at some maybe more advanced things to manipulate. Martin or Nick or Jasmine, you got any thoughts? Garrett, anything you tried, either from here or from the beginning that was different? Unfortunately, I'm not sure this is going to go in a really nice pattern. Notice we're making more stuff here and nothing nice is happening with it. Things aren't disappearing. So it's starting to make me a little bit nervous. This stuff does take practice, so getting a little bit better as we go along is good. It's the goal. But yeah, I mean, we could grab that, turn the cosine squared into 1 minus sine squared t, but that's not going to reduce with anything or cancel with anything. It's just going to give us another term. Yeah. So this one's a little tough. And one of the reasons I think this one's a little tough is because when we look at our original problem, notice there's no subtractions and there's no squares. And a lot of our tools, our Pythagorean identities, our cosine squared x plus sine squared x equals 1, turns into, we often use it more in the 1 minus cosine squared x format, or our other Pythagorean identities like 1 plus tangent squared x equaling secant squared x. We could certainly look at as tangent squared x equals secant squared x minus 1. So particularly these ones, I'd really like them to have subtractions with them instead of adding with them. And I'd like some of those trig functions to be squared. That would give me some extra manipulation power. So I'd like to make some of that happen. And there's a really interesting tool that's in your guys' background that comes up surprisingly often when we do these. And it's a tool that you guys know, you've used, you've seen, but one that would probably not immediately occur to you guys. If you might remember back when you were learning how to factor, if you had, let me actually start the other way. If you had something that was, say, x squared minus 25, and somebody said factor that, those were nice factoring problems. They didn't have that middle term. And the fact that they were both squared and a subtraction was super handy, right? These even had a name. They were called difference of squares because it's the difference, the subtraction of two squares. And they factored super nice into x minus 5 and x plus 5. And that plus and minus is what made that middle term go away. The negative 5x plus positive 5x going 0x made that middle term disappear. You may or may not remember that these were called conjugate pairs. Conjugate pairs. The A minus B, A plus B, the A minus B, A plus B were called conjugate pairs or just conjugates. Because when we multiply that together, we always get that nice A squared minus B squared. So why is that relevant? Well, you might notice up here, this is a difference of squares. Sorry about that. This is 1 squared minus cosine squared. So this is 1 plus cosine x times 1 minus cosine x. Similarly, this Pythagorean identity, or this version of our secondary Pythagorean identity, this works with the secant cotangent one as well. This is also a difference of squares. It's secant squared x minus 1 squared. So this is secant x plus 1 times secant x minus 1. So we might not have either of the Pythagorean identities or either of these Pythagorean identities in this problem, but both of these are one of the conjugate pairs that make up are Pythagorean identities. So it doesn't have the square we'd like, it doesn't have the subtraction, but it has potential. So one of the tools that we often use in manipulating trig functions is if we see something that either is or is part of or is like one of these conjugate pairs, putting in the other piece of its conjugate pairing can often bear fruit. So with that observation in mind, we can do one of two things. We could either multiply this numerator by this 1 plus cosine t. We could multiply that by 1 minus cosine t. Now we'd have to do it on the top and bottom. And that would turn that numerator into 1 minus cosine squared t over stuff. And that 1 minus cosine t would turn into, well, just sine squared t over stuff. And as long as that stuff works out nice, we've done something nice with the bottom, and hopefully things will interact. So that's one choice, and not a bad one. The other choice, oops, is to just erase big pieces of the problem. That always makes it better. The other choice would be to use the conjugate of the denominator. Multiply it by 1 minus secant t. Now, that's opposite of this, so we're going to have a negative sign issue, but that we can fix. And we'd have to multiply the top by the same thing, 1 minus secant t, and then have a similar kind of pattern take effect. Of the two, we'd have the bottom turn out nicer, and the top, we'd have to see what happens. I like this choice better because it's going to turn our denominator into one term and keep our numerator multiple terms, as opposed to having our numerator one term and our denominator multiple terms. So given the choice between a over b minus c versus b minus c over a, I'd much rather have a one-term denominator, because we can turn that one-term denominator, we can divide it up into both of those to start performing operations. Over here, we can't do the same thing. We can't do the a to those pieces. It doesn't work. So given the choice to simplify a numerator versus a denominator, I'm generally going to try to simplify denominators. Does that seem reasonable? Does that mean that's the right way to go on this problem? I don't know. I'm just trying stuff. I've never done this problem before, but hey, I see a conjugate pair possibility, so I'm going to go for it. That is going to turn that denominator into 1 squared, but 1 minus secant squared t. And that numerator, I'm going to leave alone for a second. I hope that numerator is going to turn out, plus. I hope that numerator is going to turn out worth it, but let's just wait and see what happens. Because we do have to do something a little bit slick with that denominator here. That's actually kind of what makes me nervous about this problem, is there's a couple of slick things I'm doing here. If we factor out that negative, we can reverse the order of that subtraction so that it matches our identity. So that's going to turn our denominator into a negative tangent squared t. So kind of a lot happened there that needed to be a little bit funky manipulated, but it all depends on how that top turns out. If the top turns out to be something that we can pull together, then I'll call it worth it. If the top gets messy, then we'll have to figure something else out. But questions about those steps on the bottom. I know this is a tough one. I did grab this one from your homework. I notice your homework ones generally aren't bad, but sometimes just by the randomness of how they're put together, sometimes they're a little bit, nastier, and sometimes they're, not as nasty. So I really do recommend you kind of do that. Give me a similar exercise and go through a handful of them. If you're like, oh, I don't need to practice, these are easy, then doing a bunch more won't take you much time. If you're fighting with these, then doing more of them will get you more practice and more experience. So you do want to spend time with these manipulations. Because frankly, watching me do it is only so helpful. Because it's about what you're seeing and what you're trying, not just does it make sense that we can do that. Okay, I've been putting it off long enough. We got to do something with that numerator. So FOIL, right? So got to multiply those together. So 1 squared minus cosine times what? FOIL. Just to make sure I'm using the right order. So first outer, so that's going to be negative secant t, and then inner, so plus cosine t, and then last cosine times secant. What's cosine? What's cosine times secant? Tell me down in the comments. What's go in the chats? What's cosine times secant? Nicholas, yeah, it's 1. -1 in this case because the secant's negative, but secant and cosine are reciprocals of each other. So multiply them together. It's like 5 times 5 times 1/5. They're reciprocals, so they just turn each other into a 1. Well, and that's kind of nice because it is going to make these 1s go away. I was a little bit concerned about that 1, so that's good. So we're left with a negative secant t plus cosine t. Okay, all those negatives are bothering me. So I don't like them, so I'm going to get rid of them. So I'm going to multiply that negative up there. It's going to turn our tangent into a positive. And turn the secant into a positive and make the cosine negative. So positive secant t minus cosine t. I just think that looks better, and I'm less inclined to randomly lose some negative somewhere if I do that. So, okay, maybe that was super helpful. Maybe it wasn't super helpful, but it did get rid of in both cases, got rid of the 1 plus that was problematic. And it did turn that denominator into 1 term, which is nice because then we can divide it up into those other 2 terms. The tangent squared makes me a little nervous. Not sure quite what's going to happen with that. But that's why we're here, to play with that kind of stuff, right? So let's keep going in this path and divide that tan squared up into both of those. That's going to give us a secant t over tangent squared t minus cosine t over tangent squared t. Almost hate to do that. I had got it down to 1 term. Now I'm breaking it up into 2 more terms. I guess we wouldn't have to do that. we could combine like terms in that numerator instead. But I started this way, so let's keep going this way. Let's see. Secant is 1 over cosine t. Tangent is sine over cosine, so that's going to be cosine squared over sine squared when we multiply by its reciprocal. Because remember, tangent is sine squared over cosine squared when tangent squared. So multiply it by its reciprocal. That's going to get those cosines to go away a little bit, so that's nice. We're going to have a cosine t over sine squared t. Over here, going to do the same kind of thing. That cosine is going to be a cosine t over 1 multiplied by this thing in its reciprocal form. Ooh, that's going to get messy. Cosine squared t over sine squared t. Gotta move my little chat box here. That's going to give us what? Minus cosine to the third. That makes me nervous. T over sine squared t. So cosine t minus cosine to the third t all over sine squared t. Sorry, I'm being inconsistent with my parentheses on those t's, but either way is technically fine. So that cosine to the third might make us nervous. Gosh, I wish it was a cosine squared instead of a cosine cubed. Well, if I want that, maybe I'll make that. It's a cosine in both of those terms. So let's factor it out. 1 minus sine, sine. 1 minus cosine squared t over sine squared t. Okay. Well, we isolated that 1 minus cosine squared t. What's 1 minus cosine squared t? Shay, I heard you say sine squared, but I'm going to pick on you because what did you not say?
Sine squared t.
Sine squared t. You might have said t and I missed it. It's hard to read lips, but now be careful of that habit. It does tend to bite people, particularly when you're not in class and saying this stuff, and I can't get on you guys every time you don't say the argument. So you really got to fight with yourselves to make sure that happens. So 1 minus cosine squared t is sine squared from our base Pythagorean identity. So hey, we're just left with cosine t. So this whole thing's equal to cosine t. Now that was a really long, convoluted path. Is there an easier way to get that problem down to cosine t? I have absolutely no doubt that there was a nicer way to do that. Actually, maybe there's not a nicer way to do that. I don't know. Did I know that was going to happen? Absolutely not. I hoped something would happen. And that's the key to doing these, is just kind of go, gosh, I don't know what's going to happen, but let me try stuff and just kind of messing around with it and playing around with it and go, I don't like that. I'm going to make it into something else, or ooh, see if I can build this so I can use this identity, and just seeing what happens. I gotta be, honest with you here. When I went right here, I got really nervous for a second. Like, cosine to the third, that's going to be, I got another cosine. That'll work because I'll factor it. Okay, cool. So I got a little nervous with this one. But hey, it worked out. So the danger with these problems is when you're just faced with this and it says simplify, trying to look at that and go, what am I supposed to do to make that work? You're not going to come up with this entire path. Oh, clearly that's going to happen. But often people want that, so they just stare at it, hoping to figure out some inspiration drops from the trig fairy and just ugh. And you can't do that. You have to just dive in and play with them. Does that make sense? Anybody want to try something else before we go on this problem? In the future, by the way, for these, I'm happy to, if you guys have like, hey, here's one that, can we look at what to do? And I'll be happy to do it. But this is the last time I plan on kind of going through these in this much detail. So, because we could talk about these problems for days and have fun with those conversations, but anything else anybody sees in there that they want to try or look at, or Sam, you said something before about liking kind of the grabbing common denominators thing. And I think it was Dominic who wanted to turn that into cosine t. And then we multiplied by cosine t to get that to go away. But the other thing we could have done is gotten common denominators down there, turned that into cosine t over cosine t plus 1 over cosine t. That would turn into 1 plus cosine t over cosine t plus 1 over cosine t. And then multiply that up, multiply by its reciprocal. That would give us a cosine t plus cosine squared t over cosine t plus 1. So that's where that path would lead. Not sure what I would do from there. Oh, sure I am. This is much better. We'd get cosine t times 1 plus cosine t over cosine t plus 1. And those cosine t plus 1s would cancel, even though that order is different. And we'd have cosine t. So that's a nicer path by freaking far. But either one's okay, right? And we probably could have done that if we'd have followed the other one. I think I just didn't see it. Yeah, because if you did it that way, you'd still have that cosine t plus cosine squared t over cosine t plus 1. And that same factoring would have happened here. I just didn't notice the factoring. So I had to go a different direction. Oh no, I got to talk about something really long and cool. But frankly, I wanted to talk about conjugate pairs, so it gave me an excuse. So these can be crazy at first because there's a lot of manipulation. There's a lot of moving stuff around, and it can be kind of overwhelming at times, as well as just blanking, like how would I ever start that, or how would I know to do that? It really does go play with them. It's really helpful if you've got somebody you can play with them with, so you can bounce ideas back and forth. I know that's hard under our current format, but you guys are the savviest of my groups. So you guys, have done some Zoom chats and whatnot on your own. So getting together and coming up with plans and trying to find values for these things can be really, really helpful. If you're wanting to play with them some on your own, either together or just on your own a lot, and getting stressed about, I do a manipulation, but I'm not sure if that manipulation is right. So let's say you go from here to, well, I don't know, here, and you're going, well, I'm not sure if those two things are the same. I'm not sure if the manipulations I did are allowed. One of the things you can do is just graph them. Go to either your calculators or even better, go to Desmos and put that into Desmos, put that into Desmos. If they're equal, they should land right on top of each other. Then you know all your manipulations were correct, at least legal. Fair? So you could check that. Even in this, it'd be irritating maybe to graph all of these, but you could check every statement, every step along the way and make sure, is this a legal step? I'm not sure. Well, graph it. If it graphs on top of itself, it's a legal step because they're equal. If it doesn't graph on top of itself, then no, you couldn't do that. Fair? So go play with these. We'll start working on our solving and our other identities tomorrow. Our solving does take quite a bit of time, so we'll spend a while on that. But do practice these, do play with these. Don't let them stress you out too much. If you never end up being super good at finding how to simplify these, that's not the end of the world. But what your goal is to get comfortable with the manipulations, comfortable with the fact that we can use our algebra tools to factor these things and multiply these things and manipulate them around. Starting to get that algebra and trig to talk to each other is the goal of this section. So play with that, have fun with it. If you have any trouble, let me know. If there's one you want to look at tomorrow, let me know. We'll look at it real quick and start talking about solving. Cool. Anything else I can do for you guys before you go today? Okay. Then have a wonderful day. If something comes up, let me know.